All right, guys. I want to actually answer a question that I didn't answer yesterday that Gavin asked at the end of class. He said, "Why is it that our KC expression or Q expression has the concentrations raised to the power of the coefficient as opposed to being multiplied by the coefficient." Okay, so this is our Kc d over a raised to the little a and b raised to the little b. And it's because we're multiplying, essentially. So if you think about something like, okay, so if I, for example, make this 2c, okay, then my, this is going to become 2c, but it's sort of like if we took, if we did c to the little c, and then, sorry, let me regroup here. So if instead of saying 2c, we could also write this as it like this, right? Because we've got a c and a c here. So then I would just be multiplying this by another c. Right? And if I'm multiplying these two, then it's just raising it to the 2c. Does that make sense? I don't know if that answers your question. There's also a more complicated answer to this that involves Gibbs free energy, which I am not capable of answering right now, but I will be next year because I'm going to spend the summer reviewing that for the HL content because I haven't had to teach that. So next year I'll be able to answer a little bit more of a question of how we actually derive this formula for Kc, but I am not competent to answer that question right now. But this is if this helps with the raising to the coefficients, hopefully that answers at least part of your question. Okay, so we are going to finish up this topic today. We are going to finish up the new stuff about this topic today. We'll do some. I'm going to try to pull out a demo tomorrow. We'll do some practice questions, and I'll give you some time next week to work on those questions as well as to work on your IA topics. So I'm going to put up a schedule tomorrow for you guys to sign up for one-on-one time with me to talk about your IAs. That'll happen next week while you are also working on problems. Yes? There will be a test on equilibrium. I haven't figured out what day it's going to be yet. It'll be sometime next week, but it'll be later in the week. Yeah. Okay, so the last piece of the puzzle for this topic for us is Le Chatelier's principle. And Le Chatelier was obviously a scientist who came up with this principle. And the idea is that if we have a system that's at equilibrium and we then disturb that equilibrium, we change something about the conditions of the reaction. It's going to get out of equilibrium and then try to find a new equilibrium. And we can predict what direction that new equilibrium is going to take based on what change happened to the system. And so Le Chatelier's principle says that when we have a system in equilibrium subjected to a change, that system is going to respond to minimize the effect of the change. Meaning it's going to shift the equation in the direction to counteract what just happened to shift it out of equilibrium. That doesn't mean it's going to take it back to where it was before we made that change. It's going to go into a new equilibrium position, but we can predict where that shift is going to go. All right. And an example of this is something like your thermostat in your house. Okay. If it gets too hot, turns on the AC, cools down the house. If it gets too cold, turns on the heat, heats the house. Same thing with your body. So I put the word homeostasis down here. It's a biology term, but homeostasis is trying to keep things in sort of an equal place. And your body does that with all sorts of things. Your individual cells do that with all sorts of things like pH and temperature and lots of other things. So our bodies also have a thermostat. Our chemical reactions happen optimally. Our enzymes function optimally within a certain temperature range. And so our body has evolved to figure out ways of keeping us in that optimal temperature range. So when we get too hot, we sweat and we get evaporative cooling. When we get too cold, we shiver, and that increase in kinetic energy heats up our body. Okay, so reactions are going to do, a reaction system is simpler, a lot simpler than that, but it's going to do the same thing. If whatever imbalance we make, it's going to try to shift the balance backwards to counteract that imbalance. So there are 4 things that you're responsible for knowing about changes that can happen to a reaction to equilibrium. One is changes in concentration of reactants or products. One is changes in the pressure of the system if we have gaseous reactants and or products. So we'll talk about that. It's a little bit similar to the way we talked about both concentration and pressure having effects on the rate of reaction in the kinetics unit. Pressure is only going to be a key here if we have gases. And we can also change the temperature, and that's going to have different effects depending on the reaction, and we can add a catalyst. So some of these changes will shift the position of equilibrium so that we end up with a shift towards the product side or a shift towards the reaction side. And some of these things will actually have no effect on the position of the equilibrium. And so we're going to talk about each of these changes in turn and what effect it has on where the reaction is going to go to get to the new equilibrium and whether or not that's going to change our equilibrium constant. Eva?
I was just reading that it says that you would add a catalyst once it's already at equilibrium.
Yes, but you can also, that one's a little bit weird because, and that's a good point. It's a little bit more about the addition of a catalyst at any point in time, not necessarily at equilibrium. And we'll talk about that when we get to catalysts. So yeah, the idea of the reaction already being at equilibrium doesn't apply as much to addition of a catalyst. It's a good point. Okay. So first thing, change in concentration. So we're going to talk a lot about the Haber process. I'm going to show you guys a couple videos about it. We might not get to the second one today, but I will either make some time to show it or put it in Canvas, or both. So this is for the production of ammonia. And we want to produce a lot of ammonia. It's the point of this reaction, is to produce as much ammonia as possible. But because it's a reversible reaction, at some point, if we build up enough product, enough ammonia, it's going to start decomposing back into the nitrogen and hydrogen that it came from. The reverse reaction is going to start going. So if we want to increase the amount of ammonia that we make, one thing that we can do is we can remove the ammonia that we've already made. So if we have a way of selectively reducing the concentration of ammonia, taking out the stuff that has already been made once we've reached equilibrium, then we're going to drive the reaction to produce more ammonia. Because if we reduce the concentration of the product, then there's not as much product to drive the backwards reaction, and so the forward reaction is going to take over. So if we decrease the concentration here, we're going to drive the reaction to make up for that, to make more ammonia, to make up for the fact that we pulled it out. Okay? So by decreasing the concentration of ammonia, we've effectively increased the concentration of ammonia. So that's the weird thing about these shifts, is that it's always going to try to go back against whatever perturbation you made. Yes, but Yeah.
Wouldn't that wouldn't really fix the problem, right? Because you're just going to remove the ammonia, and that's going to start decomposing by itself, right?
That's an interesting point. We can remove the ammonia and also change other conditions like temperature and pressure so that it doesn't do that. Yeah. So yeah, that's an excellent point. Yeah, that's why there's multiple processes in this in the Haber process. Yeah. So in our original reaction vessel, though, we would then start making more ammonia. Yeah. And we could, I don't know, freeze the stuff that we take out, something like that. All right. Oops. So if you look at the graph on your page 14, I'm going to give you some more examples of this when I give you some practice problems tomorrow. But being able to interpret a graph like this is going to be really important for this section, for particularly the Chatelier principle part of this topic. It's a concentration versus time graph. So like the rate graphs we've been looking at, like the graphs of the initial graphs of equilibrium looking at concentrations. And we've got time 0, time 10 minutes, and then 15 minutes. And we've got 3 things on the graph. This is for a reaction where we have hydrogen and iodine. Let's make these gases. Reversibly producing hydrogen iodide. Okay. What is happening at T0, between T0 and T10? What condition is this reaction in? It's at equilibrium. How do you know? Because Q equals Kc. Why else? What's that, Dana? Yeah, constant concentrations. Concentrations aren't changing. Okay? From that, we can infer that the forward reaction and the reverse reaction are happening at the same rate because we're not seeing an overall change in the concentrations. So we have a system at equilibrium, and then at 10 minutes, we do something to it. What is it that we're changing here first? Yeah, Brayden? Yeah, so you see this sharp increase here? That is indicating that we just dumped in some hydrogen. Okay? So at that particular time, seeing a sharp increase or a sharp decrease means that we, the experimenter, have gone in and changed the concentration of something. What happens after we do that? Jacob. Right. The H2 immediately starts to slowly decrease, and the I2 also, even though we didn't put any I2 in or change the I2 directly, it also starts to decrease, and our HI starts to increase concentration. Gavin. It doesn't have to go back to the exactly same place, but it is going to decrease. Why is it decreasing? Yeah, the reaction's pushing this way. So by adding H2, we're driving the reaction to the right. And thus, we're using up that H2 that we just put in, or at least some of it, to react with the I2 that's already there. And we're making some HI. So the concentration of HI and I2 are reacting, are changing in concert with the decrease in H2. And Oscar pointed out that this looks like there's a little bit of a delay here. There shouldn't really be a delay. But none of these graphs that you see, for the most part, none of them are going to be actual data. They're going to be schematics. So don't get too hung up on the little details of how the lines are drawn. But definitely pay attention to, sharp changes versus gradual changes, and the decrease versus what's decreasing, what's increasing. What does that tell you about the way the reaction is shifting? Okay. So what happens at 15 minutes? Yeah. Yep, we have a new equilibrium. the concentrations are not the same, okay? But Kc is the same. The overall equilibrium constant is going to be the same. Just to the overall ratio is going to be the same, but with slightly different absolute concentrations. Okay. Yeah.
Why does H2 end up roughly?
That's not. It doesn't always end up roughly at the same place. It might, depending on how much we add. Yeah, that's just coincidence. Yeah. It's not going to always go down to exactly where it started from because we're going to end up with a slightly different equilibrium, right? Yeah, unfortunate coincidence, I guess. Okay, so again, I'm going to give you some more examples of graphs like this so that you can be thinking about, okay, what graph would show a change in pressure? What graph would show a change in temperature? You know, things like that. So you'll have a chance to practice looking at these graphs. All right, so that's basically what we just did. We added extra H2 to the equilibrium mixture, and the shift is going to be to the right, and there is no effect on Kc. So the position of equilibrium changes, but the equilibrium constant does not change. Okay. So what's going to happen if we add Hi instead? Yeah, it's going to shift to the left, right? Because we'll have more Hi, we're going to counteract that by reacting more of it to make more H2 and I2. Yes? So like when we talked earlier about the relative concentrations of reactants and products and where like the Q versus Kc, how that is, that sort of where exactly the concentrations are versus where the equilibrium constant is. It's two different things. Yeah. Gavin? So because even though we're changing the absolute concentrations, we're changing them in the reactants and the products together. So it's going to end up in the same, the ratios of the concentrations of products to concentrations of reactants are going to be the same. Okay. All right, the next one, we can flip the page, is changes in pressure. And this is only going to affect gases. Okay. Now, this picture isn't in your study guide, but the idea here is we have a system at an initial volume at equilibrium with a certain number of gas molecules of A and B, and it takes two A's to make a B. And this is a reversible process. So we're at equilibrium at this particular volume at a particular pressure. And remember that the pressure is going to be inversely related to the volume, right? So as the volume decreases, the pressure increases. And it's going to be directly related to the number of particles, the number of molecules or atoms of the gas that we have. So if we dump in more, if we keep the same volume and dump in more particles, then we're going to have an increased pressure because we're going to have more things bumping against the sides of the container, which is essentially what pressure is. So if we externally change the pressure in a reversible reaction that involves gases, then what's going to happen is the equilibrium is going to shift to favor a counteraction of whatever we changed with the pressure. So, for example, if I take this volume and I squeeze it and I decrease the volume, that's increasing the pressure. The system is going to resolve things in a way to respond to that by decreasing the overall pressure as much as possible. And that response is going to be by driving the reaction towards fewer moles of gas. Because if I have fewer moles of gas, then I have fewer particles. And that relieves some of that pressure increase. So if I am increasing the pressure, I'm going to favor the production of fewer moles of gas. And I keep saying moles of gas because sometimes you have reactions that include solids and gases or liquids and gases. The pressure is only going to affect the gases. Solids there is a very slight effect of pressure on solids, but it's negligible for our purposes. It's not going to be enough to change anything. Yes, Nick? I'll get to that in the next slide. If we instead decrease the pressure by increasing the volume of this system at equilibrium, then it's going to favor the production of more moles of gas to fill up that space. So then we're going to drive this effect is going to drive the reaction backwards to make more moles of gas, to try to make the pressure as close to what it was before at equilibrium as possible. Okay. So we're counteracting whatever we did by driving the reaction such that it takes things in the opposite direction. Question? Oh, yeah, it takes a while to get going. Although it is finally working now that the room is warm. The first day it was really weird. Okay, so for example, in the Haber process, we start out with our reactants, our nitrogen and our hydrogen, and make ammonia. On the reactant side, these are all gases. On the reactant side, we've got 4 moles of gas. On the product side, we've got 2 moles of gas. So if we increase the pressure of the reaction system, we're going to favor the forward reaction because it's going to try to make fewer moles of gas to relieve that increase in pressure. So we're always going to go towards the fewer moles if we increase pressure, more moles if we decrease pressure. Okay. And like the concentration, this is not going to have an effect on Kc. So if I don't think, did I put the example 1 and example 2? I did. Oh no, I put the exercise. Sorry, I didn't clear the thing. So example 1 is asking you on that page, page 15. It says, what's the effect of an increase in pressure? So an increase in pressure is going to drive us towards the ammonia side because that has fewer moles of gas. Yeah.
So it drives through the one way, right?
Yeah. Increasing pressure drives us to the side with fewer moles. Decreasing pressure drives us to the side with more moles. So exercise or example 1 says what's going to be the effect of pressure increasing. It's going to drive the reaction to the right. Sorry, I should have written this as a two-way. It's going to drive the reaction to the right. No effect on Kc. Decreasing the pressure is going to drive the reaction to the left. So if we want to make more ammonia, we want to keep the system under pressure. Gavin? Yes. Yes, you would also increase the rate of reaction by increasing the pressure. So if you decrease the pressure, you would drive it to the left, and I guess your reaction rate would also go down. Okay, so there's the exercise at the bottom. It's giving us an equation for the formation of methanol. So we've got carbon monoxide and hydrogen makes methanol. And let's see. Wiley, tell us how you would answer this question. All right. Okay, so which one has more moles? Nope. How do you find the number of moles? Coefficients. CH3OH, does it have a coefficient? Nope. How many things are on that side? 1. So we have just 1 mole over here. Okay? How many moles, total moles of gas do we have on the reactant side? 3. Yeah, exactly. So if we increase the pressure, where is it going to go? Yes. Because it's going to, if we increase the pressure, it's going to want to relieve that pressure by having as few particles, as few moles of gas as possible. So it's going to drive it to the right. If the pressure is decreased, it's going to drive it to the left. Okay. All right. Changes in temperature. Next page. I see a few people still writing, so I'll pause for a second here. So the effect of the temperature change is going to be dependent on what type of reaction it is. Every reaction is going to be either endothermic or exothermic. If I have a reaction that is a forward reaction that is endothermic, then my reverse reaction is necessarily going to be exothermic, right? So the effect of changing temperature is going to depend on whether you have an exothermic or which direction is endothermic and which direction is exothermic. So if we are increasing the temperature, if we add heat, we're going to drive it in the direction of the endothermic reaction. Because that endothermic reaction is going to absorb that heat and turn it into chemical bonds, thus effectively lowering the temperature. So if we increase the temperature, the reaction tries to lower the temperature by absorbing heat in the endothermic direction. If we decrease the temperature, we're going to favor the exothermic reaction. Because we're basically giving it, we want to compensate for the decrease in temperature by creating more energy, creating more kinetic energy. So that exothermic reaction is going to generate heat to compensate for the decrease in temperature. Just like shivering is your way of adding heat to compensate for a decrease in temperature. Okay. There's a famous reaction where you can take, and we might have one of these. I have to see, Dr. Sorensen mentioned at one point that we might have this. If you have NO2 in a sealed tube, you can drive a reaction to turn it into N2O4 by chilling it, and the other way by heating it, so you can drive the reaction in one direction or the other just by keeping it in the sealed tube, because the NO2 will synthesize the N2O4, and the N2O4 will decompose to form NO2. Obviously, it's 2 NO2, but yeah. I'll see if I can find that, if we have it. Yeah, sorry. Oh, great question. So if I've got N2O4 comes to NO2, if I chill it, I drive it towards N2O4. If I heat it, I drive it towards NO2. Jamie. Okay. Yeah. So what's visible is that the NO2 is brown and the N2O4 is colorless. So you actually can see the color change. Yeah. You had a question in your, I think, the Stoic test about that involved this, but we hadn't talked about it yet. So, so the forward reaction is right.
Because, okay, wait, the boiling water is that way.
Mm-hmm.
Which means it's going to intake heat.
Mm-hmm.
So the forward reaction is because it's taking in heat.
So which side is going to be producing heat? No. Okay. So our N2O4, if we chill it, if we reduce the temperature, we're driving it towards the N2O4 side. So where is the heat? Is it on this side of the reaction, or on the product side, or on the reactant side?
On the other side.
The other side.
Yeah.
The product or reactant?
Product.
Yes. Okay. So, and this is what I like to do when I'm trying to figure these things out. Okay? Is I try to figure out where the heat is, and I treat the heat as a reactant or a product. Yeah, Nick? No. No. So sometimes you have to figure that out. Or they'll give you a delta H, which I'll show you in the next screen. Okay? So, in this case, you're told that the water, when we heat the water, it drives it to NO2. Sorry, I did this backwards. I did it backwards. Sorry. NO2. Okay. So if we heat this up, if we add heat, we're driving it towards NO2. So Liat was right. Our heat is on this side of the N2O4 because adding heat is going to drive it in this direction. Reducing heat is going to drive it in that direction to generate more heat. Okay, so I like to, when I'm thinking about the effective temperature in Le Chatelier's principle, I like to write in heat as a reactant or product, and then figure out either whether it's endo or exothermic or what direction it's gonna go in. So the forward reaction then, is that going to be exothermic or endothermic? Oh. Right. Nothing. Yeah. Okay. Yes. Connection. Okay.
What kind of reaction is lava like?
It's not a reaction. It's a physical process. Okay. So if the heat is on the reactant side, is the forward reaction an endothermic or exothermic reaction? Endothermic, yeah. So this is endo, and this is exothermic the other way, okay? And so putting it like that makes it, I'll show you in a second, makes it easier for me to wrap my head around those kinds of things. To consider heat to be a reactant or a product in the reaction, whether if so it would be a product if it's an exothermic reaction, it's a reactant if it's an endothermic reaction. Brayden. So that's a possibility. You might have a question where, like, part one is determine the delta H of this reaction by bond enthalpies. And then the next part B might be determine the effect of an increase in temperature on the equilibrium.
So in this case, it would be the heat is on the left of the reaction because there's a higher bond enthalpy on the right side of the reaction. Like the combined bond enthalpy on the right side.
Yes. Yes.
So are there like double bonds on that side?
Yeah, there are. Yeah. Okay. All right. Temperature change is the only thing that changes Kc. Okay, so everything else doesn't change Kc, changing in concentration, changing pressure, catalyst, none of those things change the equilibrium constant, but temperature does. So if we shift to the left, then we're going to decrease Kc. If we shift to the right, we're increasing Kc, which makes sense because you remember the Kc is products over reactants. So if we're shifting towards the products, we're increasing Kc. If we're shifting towards the reactants, we're decreasing Kc. And this specifically affects, temperature actually affects the overall ratio and therefore the value of Kc, because even though we are increasing the kinetic energy of all of the reaction particles, only some of them are going to, only one side is going to be positively or negatively affected. It's not like when we change the concentration, we put things back into the same ratios. Changing the temperature is actually going to change the ratios of the concentrations, and therefore is going to change the value of Kc. Okay. Oops. Keep forgetting to clear those after first period. All right, so here's an example. We have formation of CO2 from carbon monoxide and water, and we're told that the delta H is negative. We don't know negative what, doesn't matter. Is this, first of all, is this an endothermic or an exothermic reaction? It's exothermic. That means the forward reaction is exothermic, right? So if you're given a delta H for a reversible reaction, it's specifically say, if it doesn't specifically say delta H of the forward reaction, if it's just like the reaction and then you're given a value for delta H, assume that that is the value for the forward reaction. Yeah. All right. So if we decrease the temperature, which way is equilibrium going to shift? Are we going to shift to the right towards the products or to the left towards the reactants? If we decrease the temperature. So if I'm putting heat in as a reactant or a product, which side is it going on the reactant side or the product side? It's exothermic. Are we absorbing heat or releasing heat? We're releasing heat, so heat is going to be a product of the forward reaction. Okay? So if I'm making heat with the forward reaction and my perturbation is decreasing the temperature, I'm going to want to counteract that by making more heat. So I'm going to shift the reaction to the right to generate more heat. Yes? No such thing. But you could measure the bond enthalpies. You could use the enthalpies of formation or enthalpies of combustion or any of the other things that we did in topic 5. It's not a dumb question. It is just circling back around. So you will often have a multi-part question where one part of it will be determining the delta H using something from topic 5, and then the next part will ask what's the effect of a change in temperature. Yes, negative delta H is exothermic. Yep. Positive is endothermic. Yep. Yep. And again, we're assuming this is for the forward reaction unless we're told otherwise. Okay. Oops. I just want to quickly, before the bell rings, say that a catalyst does not have an effect on the position of equilibrium. It doesn't shift the equilibrium, and it has no effect on Kc, because it reduces the activation energy for both reactions, forward and reverse. So all it does is get us to equilibrium quicker. Yeah. Jacob?
Yeah, can you explain the last one again? The one before last one.
Change the Kc because I thought like Kc and the equilibrium was more like related.
Okay. I will try to explain that better tomorrow.
The way they hear, Q temporarily does not equal Kc. If you had a catalyst, that doesn't happen.
If it's already at equilibrium, yeah, nothing would really change, but it'll get you to equilibrium faster. So that's why I was responding to Ava's question earlier about if it's already at equilibrium, does the catalyst do anything? No, doesn't do anything.